Hi everyone, this is video number 12 of the Regents chemistry curriculum, and today we're going to talk about kinetics and equilibrium. Our objective for today is to increase the rate of a reaction at equilibrium and cause it to favor the production of products or reactants. So make a reaction happen faster, and if the reaction is at equilibrium, we're going to shift it to the right or shift it to the left according to our knowledge of Le Chatelier principle. So here are some questions. Please read the following statements, determine whether they're true or false. And I don't expect you to answer number 1 because you probably don't know what TCCSNP is, 2 C's, SNPs, and but you'll be able to answer the other statements 2 to 7. Okay, sorry. Now, let's take a look at our notes. So to increase the kinetics energy of a sample means to make the particles move a little faster. So, when a reaction is at equilibrium, that means the rate of the forward reaction equals the rate of the reverse reaction, and the concentration of the reactants and the concentration of the products remain constant because, again, the rate of the forward equals the rate of the reverse. There are 2 types of equilibrium. There is phase equilibrium, okay, and there's chemical equilibrium. So if we're talking about a phase equilibrium, let's say you have a flask that has some liquid water and you expose that water to heat. The liquid water will turn to gas, and the gas will turn back to liquid water. So here we have a phase equilibrium as long as this is a sealed flask. So in phase equilibrium, in this case, the rate of evaporation equals the rate of condensation. Okay. Solution equilibrium. That's when the rate of dissolving of a solute in a solvent equals the rate of recrystallization of a solute in a solvent. So we'll talk more about solution equilibrium, saturated solutions, in the next video. But today we're going to focus mostly on chemical equilibrium, and that is when the rate of the forward reaction, in other words, the rate of converting these 2 reactants to these products, equals the rate of reverse reaction, which is the rate of converting these back to these. And because the speed at which you are going to make these equals the speed at which you are going to make these is the same, if the speeds are the same, then the concentrations will remain the same. So if you started with 5 milligrams here of everything, you're going to end up with 5 milligrams here of everything. It doesn't matter how many times this goes to this and this goes to that. Okay, so with that said, let's continue. So double-headed arrow will always indicate that the system is at equilibrium. We'll talk more about voltaic cells. That's electrochemistry. In the next upcoming videos, you'll see, hopefully you'll watch a video about the voltaic cell. Just keep in mind that if a battery is dead, know that the battery has reached equilibrium. This will only happen again in sealed containers. We'll talk more about the saturated solutions in the next videos, but just know that saturated solutions are at equilibrium. because everything you're adding is going to recrystallize at the bottom. I wouldn't necessarily call this at equilibrium. I'll just say that this solution is neutral. Okay, reaction rates. Several factors can affect the system that is at equilibrium. For example, 2C's SNPs. And the TCCSNP stands for temperature, T, temperature, C, concentration, C, catalyst, S, surface area, N, the nature of the reactants or the type of reactants that you have, and P for pressure, which only affects reactions that are made completely of gases. So let's start off by talking about catalysts. A catalyst does not cause an equilibrium to shift right or shift left. It's not going to cause the equilibrium to shift right to favor the production of the products or shift left to favor the production of the reactants. So going back here, adding a catalyst to any of these reactions is not going to cause the reaction to go right or go left. Okay? It's just going to make the reaction go faster in both directions, right and left. Okay? It's going to make the reaction just happen very fast in both directions. So how does a catalyst work? It changes the particle orientations. Very important for us to know that a catalyst is going to change the particle orientations. That's number one. Okay. And provide an alternate collision pathway. So this will be number two. When you change the particle orientations and provide an alternate collision pathway, you are going to lower the forward and reverse activation energies. So in the previous video, we talked about, I think it was video number 11, we talked about potential energy diagrams. And when you add a catalyst, you're only going to lower the forward and reverse activation energies. So the energy needed will no longer be this much. The energy will now be only this much. Same thing in the reverse directions. The energy needed to drive the reaction in the reverse direction will not be that much. It will only be this much. So a catalyst lowers the activation energy. The collision theory states that a reaction takes place when reacting particles collide with sufficient energy and proper orientation. So you're not going to have a chemical reaction unless the particles are colliding with sufficient energy and proper orientation. Think of you clapping. If your hands are not aligned correctly and you're not moving your hands with sufficient energy, you're not going to be able to hear you clapping. Nobody's going to be able to hear you clapping. So sufficient energy and proper orientation are necessary. The more collisions, the faster is the reaction rate. So let's talk about temperature now. If you increase the temperature, you will increase the motion of the particles, and more particles moving means more chance of collision, and a higher chance of collision means a faster reaction. Concentration again, more particles per unit area. If you have a lot more particles, there's a higher chance of collision. Higher chance of collision means a faster reaction. Surface area, obviously a powder will occupy a lot more space than a solid, so powders have a much larger surface area, and therefore they're more likely going to, if you have a powder substance, it's more likely going to cause a lot more collisions with whatever other substance you mix it with than if you have a solid substance. Nature of reactants, it's very important to know that ionic compounds, if you are using an ionic compound, let's say NaCl, and you dissolve that in water, an ionic compound will dissociate. The positive will attract to the oxygen part of the water, the negative and the chlorine will attract to, chlorine is negative, it will attract to the positive part of the water, the hydrogen. So this dissociation will create a lot more collisions, because now it's not just NaCl that's colliding, it's Na that's colliding and Cl that's colliding. Moving on to pressure. So pressure is going to force gas particles to occupy a smaller volume. And it's kind of like, think of gas particles all over the place in this container. And now you are going to press these gas particles using a piston to make them occupy only this space. So now, of course, there's less space for them, so they're more likely going to collide and make a reaction happen faster. Okay, now Le Chatelier principle. So Le Chatelier just talks about how a reaction can shift to the right to make more products, or shift to the left to make more reactants if it is exposed to different stresses. So let's take a look at this. Le Chatelier principle helps us predict the effect of applying a stress on a system. Increasing the pressure on a reaction made entirely of gases will cause the reaction to shift to the side with the least total number of moles. So, taking a look at this reaction, if I increase the pressure on this reaction, nothing will happen because this reaction is not made entirely of gases. So sodium is a metal, it is not a gas, and sodium chloride is a solid. So increasing the pressure on this system will not cause this reaction to move either to the right or to the left. However, let's say I had N2 plus H2 to yield NH3, and this reaction was at equilibrium. Make sure, let's balance this equation very quickly. So here we have 6 hydrogens in both directions. If I increase the, and this is all gases, nitrogen is a gas, hydrogen is a gas, ammonia is a gas. If I increase the pressure on this system, the reaction will shift to the side with the least total number of moles. So in this case, looking at this reaction, we see that ammonia, there are 2 moles of ammonia here, which means that this side of the reaction has the least total number of moles, while that side of the reaction has a total of 4 moles. There are 3 moles for hydrogen and 1 mole for nitrogen. That gives me a total of 4 moles. So increasing the pressure on this system will favor the production of ammonia, while decreasing the pressure on this system obviously will favor the production of H2 and N2. What does that mean? If I'm favoring the production of ammonia, that means the concentration of ammonia will increase and the concentrations of hydrogen and nitrogen will decrease. I'm going to have less and less hydrogen and nitrogen. Okay? So that's it about pressure and how it only affects gases. Let's continue on. Let's talk about temperature. Increasing the temperature on an exothermic reaction will cause the reaction to shift towards the reactants. Increasing the temperature on an endothermic reaction will cause the reaction to shift towards the products. So let's take a look at this reaction here. We have the production of sodium chloride, table salt. Obviously, this reaction is exothermic because we are releasing heat. The heat is on the right side of the reaction, so we're releasing heat. Now, if I increase the temperature on this system, the reaction is going to shift towards the left, which means I'm going to be producing more and more Na and more Cl, and I'm going to have a lot less NaCl salt. So this decreases while these two are going to increase. Okay. Now, when you add a substance to a reaction that is at equilibrium, the equilibrium will shift away from whatever that substance is located on the given reaction. So, let's say, for example, here, if I increase the concentration of NaCl, the system will shift away from wherever NaCl is on this reaction. So that means the system will shift to that side. What does that mean? That because I increased the concentration of NaCl, my temperature is going to drop, my energy is going to drop, and I'm going to produce more and more of chlorine and sodium. On the other hand, if I decreased the concentration of, let's say, chlorine, if I decrease the concentration of chlorine, when you remove a substance from a reaction, the equilibrium will shift towards whatever that substance is located on that given reaction. So here's the given reaction. When I remove chlorine or decrease the concentration of chlorine, the system will move towards chlorine. So the system will shift that way. What does that mean? That means that everything here is going to drop, is going to decrease, and then Na here is going to actually increase, and chlorine is going to be replenished to restore equilibrium. So here's more about what I just said, and that's pretty much it. So let's go back to the questions. Read the following statements, determine whether they're true or false, and that's pretty much it. Thank you.